Okay, now we're going to move on to more of a calculation area of the course. It's called the ratio of surface area to volume. So my purpose here is, what you're finding with a lot of this course, simple notes, reading the textbook seems to be sufficient. There is a property with cells where you really need to consider the efficiency, and it says here, as an efficient open system, the cell must be able to carry out all the life processes. The transport of materials into and out of the cell is critical. Basically, the cell has to operate in the most efficient manner possible. But then there's the issue of size. And now I'm on the right-hand side, and it says if a cell becomes larger, that means its volume increases. More molecules will need to be transported across the cell surface to take part in the cell's function. If the cell is to maintain its ability to transport substances, there must be a greater surface area to match the increased need for molecule transport. So basically, what I'm trying to say here is, as a cell becomes bigger, that increases the volume, but then so does the surface area of that cell. And it's all about right here. For efficient transport, the cell must have a large surface area in relation to its volume. High surface area to volume ratio equals greater efficiency. Again, you can read about this in the book, but what I'm here to tell you about is how to do the actual calculations. If you look right here, okay, if you look, just some basic, little examples here. Is you have a small cube. It's a 1 millimeter cube. So you have six. So each side is 1 millimeter. So if you have 6 sides on a cube, that's 6 millimeters squared in total surface area. The volume is length times width times height, which would be 1 times 1 times 1. In that case, you get a 6:1 surface area to volume ratio. And then you can see the other examples here as well. Okay, surface. So again, I'm trying to show you here which one of these is better. You look over here on the other side, you can see this surface area. You have one large cell. Okay, surface area of one large cube is 5,400 micrometers squared. If you look at this one, okay, it is so many small cells put together. Total surface area of 27 small cubes is 16,200 micrometers, okay? So it seems to be, if I go back over here, okay, if I just go back one, remember, for efficient transport, the cell must have a large surface area in relation to its volume. So if you look here, okay, and here, I can't draw very well, essentially the volume is the same, but what has changed? This one has a large surface area because it's a whole bunch of small cubes put together. So each of those cubes has 6 sides. They're so much exposed. That's going to be a more efficient system. So again, you want to have a large surface area to volume ratio. Now, I'm going to help you calculate some of this. This is an example from your book. It says, determine the surface area to volume ratio for a cube with a side length of 3.5 centimeters. So it's a cube, which means every side is the same, which is nice. The first thing you're going to want to do is find the surface area. So what I do is I find the surface area of one side. This is just one side of that cube. And each length is 3.5 centimeters. I undergo a basic example. That gives me a surface area of one side of 12.25 centimeters squared. Then, of course, I multiply that by 6 because that will give me the surface area of the entire cube because there are 6 sides. The next part is easy, is you find the volume of this cube. Volume is length times width times height, so 3.5, 3.5, 3.5. That gives me 42.875 centimeters cubed. To find the surface area to volume ratio, well, all you do is you take the surface area and you divide it by the volume. It's 1.7. That's a pretty straightforward example because, you see, in this case, it's a cube, When you have a cube, you know that every side is exactly the same, and you can undergo this calculation. Life is a little more complicated when this time they give you a rectangular prism. Now this is very much junior high math in regards to measurement. Because what you have in this case is, again, I'm sorry my drawing is not probably that great. Maybe I'll draw it at the top right here. So what you have is a three-dimensional object, and you have nothing's the same. So if you look at this, let's say this is the length. The length is 2.5, okay, centimeters. The width we'll call right here is 2.0, and the height is 1.0. So what you have to do, if you remember back to junior high math, you have to calculate the area. So you go top and bottom. So we'll do that one first. So the top and bottom. So that would be like looking at this part right here. And you want to find the area of that. So area equals length times width, or base times height. So that's going to be now 2.5 centimeters times, so that's 2.5 in this dimension, and 2.0 in this dimension. So you're going to take out your calculator, you're going to go 2.5 times 2, which is 5 centimeters squared. But you got to be careful. This is top and the bottom. So the top of this prism is 5, and the bottom would also be 5. So what you do is you go times by 2, so in total you have 10 centimeters squared. Then let's look at the front and the back. Area equals length times width. So we're looking at the front of this prism now. So it's going to be 2.5 centimeters times 1.0 centimeters. That's going to give you 2.5 centimeters squared. Now again, we have a front, we have a back. So, okay, that's going to give us 5 centimeters squared. Then you have the sides, side and side. So we're now looking at the side here. So that's going to be area equals length times width equals 2.0 centimeters times 1.0 centimeters. This dimension, that's going to give you 2.0 centimeters squared. Now remember, you have two sides, so multiply that by 2. That's 4 centimeters squared. The final step is you have to figure out your grand total for surface area for the entire structure. So I'm going to go total surface area. All you have to do is add those together. That is 19 centimeters squared. Now, of course, we need the volume. I don't mean to confuse anyone here, but what I'm going to do is I'm just going to erase and give us some space. I'll erase maybe over here. Maybe one more. Actually, I'll just erase. I think, because you can rewind this, obviously, on your device. So what I'll do is I'll kind of do a bit of a... I'll even get rid of that. I'll go... So we have a surface area of 19 centimeters squared. Now we'll do our volume. Volume is always the easy one because it is length times width times height. So that's going to be 2.5 centimeters times 2.0 centimeters times 1.0 centimeters. So that should give us 5.0 centimeters cubed. Okay, now we'll do our ratio. The ratio is surface area divided by volume, which should give us 19 centimeters squared divided by 5.0 centimeters cubed. We really shouldn't worry about the units. This is probably one of the few times in science where someone will say to you, don't worry about the units, but it's actually true in this case because we're just worried about the ratio. We don't want any units associated. So, let's see here. All we have to do is go 19 divided by 5, and I'm messing up on my calculator, so I'm doing two things at once. That gives us a ratio of 3.8. That would likely be one of the more difficult calculations we would have to do. I would suggest maybe rewatching this example. And just remember, you want to read this part in the textbook and just understand about, you really, really want to focus on, some questions might say to you, well, which ratio is better? Which one's more efficient? And it really comes back to right here. For efficient transport, the cell must have a large surface area in relation to its volume. I hope that makes sense, and please try some practice questions.